We've done the first question in the worksheet named L1. Now we're going to do the second question in L2. So before I start, I'm going to copy these questions here. I'm going to copy these questions to Excel. Right? And then I'm going to answer the questions over here, right? So in my particular version of the question, I have 512 students in a college stats class. They're asked to stand with a quarter in their palm and toss it. If they get tails, they remain standing. Sorry, if they get tails, they sit. If they got heads, they remain standing. And this experiment continues until only one person is left. Okay, so everything that follows here is not what we observe, it's what we expect, right? What we observe and what we expect are two different things. Over the long run, they become the same, right? Over the long run, if we do this infinite many times, the two will become the same. But when we do this once, what we observe and what we expect will be two different things. Now, how many people are standing prior to the first coin flip? In my case, 512, because I have 512 students in this particular class. You're going to have a different number, right? And then the next question is, how many people do you expect to be standing after the first coin flip? So if 512 people flip a coin, we expect half of them to get tails, and we expect half them to get heads. So we expect half of them, right, to be left standing. So 256, right? So we start with 512. After one round, we expect 256 to remain standing, right? After the second coin flip, well, we expect half to get heads, and we expect half to get tails. So we expect half the 256 to remain standing, right? That's 128. Okay, what about the third coin flip? After the third coin flip, right? 128 people flip a coin. We expect half to get heads, half to get tails. We expect half of them to sit and half to remain standing, right? Et cetera, right? Until we get down to one. After the ninth coin flip, in my particular case, there'll be one person standing. That's what we expect, right? We expect 9 coin flips, one person standing. Now, in reality, there could be 0. In reality, we could observe 3. In reality, we could observe 4. But we expect 1, right? We expect 1. So each time we're halving this total, right? So this is 32. This is 16. This is 8. This is 4. This is 2. This is 1. Now, what about the 10th coin flip? Okay, so if there's one person standing after the 9th coin flip, what do we expect to happen on the 10th? Well, that person could get a head, or that person could get tails, right? Heads or tails, right? So we expect that person, we expect 0.5 people to be standing after the 10th coin flip, right? So this last one here is 0.5. Now, the next question is, we need to find this box here, right? Blank rounds are when the expected number of students standing equals exactly 1. So in my case, that would be 9. 9 rounds are when the expected number of students equals exactly 1. Now, the probability of getting that many heads in a row is what? Okay, so let's look at this one person who's left standing after 9 coin flips. So X here is equal to 1, 2, right? 9 coin flips in a row, right? Got a heads, 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 right? So we get type H here, type H here, right? And that person would have, if this person had, another way to think about this, the person could have 9 quarters in their hand. That person throws those 9 quarters in the air, and all 9 quarters result in heads. The probability of heads for the first coin is 0.5. And that's the same for all 9 coins, right? So we can think of this as nine consecutive heads, or 9 coins from the air and all landing on heads, right? So if we think of it as 9 consecutive coins, we can think of it as heads on the first, and heads on the second, and heads on the third, and heads on the fourth, and heads on the fifth, and heads on the sixth. We're talking about mutually exclusive things, right? Or independent. We're talking about independent events. Whether I flip a heads, if I flip a heads on the first, that has no bearing on what I get on the second toss. So we're talking about 9 independent events. And when we're talking about independent events, and we're talking about and the intersection of these events, we can multiply these probabilities together, right? So in order to get the probability of heads on the first, and heads on the second, and heads on the third, et cetera, and heads on the 8, and heads on the 9, all we have to do is multiply these probabilities together. We can do that easily in Excel with product, parentheses, and then highlight the 9.5 probabilities and hit enter. Another way to calculate is to raise 0.5 to the 9th power, right? So the probability to 4 decimal places is 0.0020. So now we want to calculate the probability that not only does one person gets all heads, 512 get heads. So the way we think about that is we have 512 students. The first student gets 9 heads in a row. The second student gets 9 heads in a row. The third gets 9 heads in a row. And the fourth gets 9 heads in a row. And the fifth, et cetera. And the 511th gets 9 heads in a row. And the 512th gets 9 heads in a row. What we have to do there is we have to raise this to the 512th power, right? We have to raise this. We have to multiply that probability by itself 512 times, or raise that number to 512. And we get something really close to 0. I mean, it's really close to 0. Let me increase the number of decimal places. It's really close to 0, see? It's essentially 0, right? Really close to 0. To 4 decimals, it is 0, right? Though the probability of 512 students standing after that many rounds is 0.0000, yada, 00, whatever, right? Is it possible that all 512 students can be standing? It's possible, but it's really, really unlikely because the probability of it is so close to 0, right? So it's possible, but very, very unlikely. So for the next question, we're going to take a screenshot of this tree. I'm going to paste it into my problem here. I'm going to highlight these cells and color them white. I'm going to put a box around it. I'm going to kind of center that. Okay, and then R1 is the event. Your customer's first selection was a red balloon. B1 is the event. Your customer's first selection was a blue balloon. R2, the customer's second selection was a red balloon. B2, the customer's second selection was a blue balloon, right? So we have, initially, the store has 2 balloons that are blue and 3 balloons that are red, right? If a blue balloon is taken, the customer's second choice, that person's left with what? 1 balloon that is blue and 3 balloons that are red. If that customer's first choice is red, that customer's left with 2 blue balloons to choose from or 2 red balloons to choose from, right? We're going to use this diagram and the conditional probability rule definition to answer the questions below. Now, the first question is what? The probability that a blue balloon is taken second, given a red balloon was taken first. Okay, so a red balloon is taken first. That puts us on the lower branch down here. A red balloon's taken, right? That leaves 2 red balloons in the store and 2 blue balloons, right? So with this balloon gone, the probability of getting a blue on the second is what? 2 and 4. So this is just 2 divided by 4, right? 0.5. Okay, now to get this answer, the probability of red on the first choice and blue on the second choice, the probability of that, we have to use the conditional probability rule. So we have the probability of B2 given R1, right? That equals this right here equals, using the definition of conditional probability, it equals B2 and R1, right? The probability of B2 and R1 divided by the probability of R1, right? That's the conditional probability definition. We know this, and the tree says that's 3 divided by 5. The thing we don't know is this part, right? So we're going to use some algebra. We're going to multiply both sides by the probability of R1, right? So that cancels on the right, and we're going to move it to the left, right? We're multiplying both sides by that value, right? Okay, then I'm going to move this over to the right side of the equation. So we want to know the probability of B2 and R1, which is this here, right? That equals what? The first part is the 0.5, right? The second part is the probability of R1. Well, that's 3 divided by 5, according to the diagram, right? So 3 divided by 5. Right here, right? There's 3 red balloons and 5 total balloons to choose from initially, right? So that means the probability of B2 and R1 is 0.3. In order to get the joint probability, we multiply the probability on this branch times the probability on that branch. So let's pull this down. We're going to change this to R1 and R2. Well, we can say that it's R2 and R1, right? It doesn't matter. We're going to change this to R2. And then we have R1 times, yeah, there we go. Okay, so now the probability of R2 and R1 is the probability of R2 given R1, right? Times the probability of R1. The probability of R1 is this 3/5, right? So we've chosen red first, right? Leaving us with 2 red and 2 blue. The probability of R2 given R1, that's this 2/4. So we multiply this 2/4 times that 3/5. And notice it's the same as the previous probability, right? It's the same. We had 10 marbles in here, right? We have 9 marbles here, we have 9 marbles here, and all these numbers would be different, right? So it just so happens with this particular example that these two numbers are the same, right? Because we have 3/5, right? 3/5 times 2/4, right? We're multiplying this probability times that probability to get their joint probability, correct? 0.3. The next thing we want is the probability of R2 and B1, right? So I'm going to change the R1 to B1. Now, the first thing we did is we pulled out a blue. So that means the probability of pulling out a blue initially is 2/5 because we had 2 blue balloons and 3 red balloons, and 2 plus 3 is 5. So we have the probability of pulling out a blue balloon is 2/5, right? So the first part of this calculation is 2 divided by 5. Then we need the probability of R2 given B1. So we're in this situation. A blue is taken first, meaning we had 2 blue balloons. Now we only have 1. We have a total of 4 for our second choice, right? And we want to know the probability of pulling out a red on our second choice. We have 3 red and 4 total balloons, so 3/4. This number here is 3 divided by 4. This probability is 3 divided by 4. And we get what? Again, we get 0.3. Now, this is all coincidental because of the way the problem's set up, right? We have 5 balloons. If we had 100 balloons, we'd have 99 here, 99 here, and these would probably not be the same, right? This is a result of this particular problem, right? So again, it's 0.3 here. Okay, so next we want to calculate the probability of this is an event here, right? R1 and R2. R1 and R2, its probability is 0.3. And then we have this event, B1 and R2. B1 and R2, and its probability is 0.3, right? Now, is B1 and R2, that event, mutually exclusive, right? With R1 and R2. If I'm a customer, can R1 and R2 happen at the same exact time as B1 and R2? No, it can't, right? So this intersection event and this intersection event are mutually exclusive. They can't happen at the exact same time, right? So all we have to do is just add these two probabilities because we're looking at the union here, right? So 0.3 plus 0.3 is 0.6000, right? So down here, I'm going to pull this. So I got R1 and R2, right? I'll use squiggly brackets in here, right? Then I got or, right? And squiggly brackets. And then I got B1 and R2, right? So all I gotta do is add these two together. R2 and R1 plus B1 and R2, and I get 0.6. Make sure you show your work, right, in your spreadsheet, because I'm going to be grading it. In question 3, we want to answer these two questions, right? If two events are mutually exclusive, the probability of both events occurring simultaneously is 0. They're mutually exclusive, right? If we go back to this original example here, in my first problem, I had a spinner with 16 spaces, right? Can I spin a 1 and 2 at the same time? 1 and 2 can't happen at the same time. The arrow either lands on 1 or it lands on 2. It can't land on both at the same time. So 1 and 8 are mutually exclusive. Any pair of these numbers are mutually exclusive. So the probability of it landing on 1 and 14, that probability is 0. If two events are collectively exhaustive, the probability of one or the other, right? Let's do this. Let's change this to 2 numbers. And let's go back to the question. If two events are collectively exhaustive, the probability of one or the other is what? What's the probability of one, x equal 1, or x equal 2? Well, the probability of x equal 1 is 0.5. The probability of x equal 2 is 0.5. The spinner can't land on both 1 and 2 simultaneously. So these are mutually exclusive. So the probability of x equal 1 or x equal 2, well, that's equal to, that union, right, is the sum of those two probabilities, 0.5 plus 0.5, which is equal to 1, right? So 1 and 2 are collectively exhaustive. And when two events are collectively exhaustive, the probability of them is 1.